Well, it's 6 p.m. This is the randomizer for January 31st, Monday, 2022. And tonight's randomizer is going to be about thermionics. I'm Charles Schultz, and head of Schultz Laboratories and the Universe Science Center. And this is our weekly 6 p.m. randomizer talk. The subject that was randomly selected by the machine this time around is thermionics. What is thermionics? Okay, well, just imagine if you had an electrical generator and it didn't have any wheels or magnets or turbines, no moving parts, didn't have anything complicated happening. It just made electricity from a difference of temperature, from heat and cold. Thermionic devices can do this. And it's sort of a mystical subject to people because they don't see these things, but they've been in use for quite a while. The reason you don't see them a lot is because the efficiency has not been very good. So let's go back a little bit and understand what thermionic emission is. Just like water can evaporate, electrons can evaporate off of atoms. You've often been in a hot shower, stepped out of the shower, and instantly it seems like you're covered with cold water. How the heck does that happen? Where did the hot water go? The answer is real simple. The droplets of water that are all over you have a mixture of hot and cold molecules in them. And the moment you step out of the shower, the hottest molecules have enough energy to escape the water droplet's surface tension. They evaporate away because they're moving faster, they're hotter. What's left behind? Cold water. Very simple principle, evaporative cooling. Now imagine you have a bunch of metal atoms, and these metal atoms have a property of not binding to their outer electrons very strongly. They're only weakly held, like around a volt or so. And imagine you heat up the metal and apply a little bit of a voltage charge nearby. And the electrons want to escape to that voltage charge, and they ping off of the metal and off they go. Well, then you have a flow of electrons, and electricity, basically, current is a flow of electrons, charged particles. So if you have a metal plate in a vacuum tube, and you heat it up, and you have another plate over here that's charged positively, those little negative electrons will come flying off of it from the heat, be emitted and captured on the other side. And that's basically a diode, but it's the root of thermionic generation. So let's look a little at what happened. Where did it come from? Who discovered it? A lot of people don't like Thomas Edison because he did have a lot of shifty things in his background. And nevertheless, he did actually invent and discover certain principles. And the thermionic principle was found by Thomas Edison in his lab. And how it worked was very simple. Edison was really taken with the light bulb, and he didn't know what could be done to moderate its operation or alter it in some way. And like any tinkerer, he experimented. And one of the things he did is he had the light bulb, which is basically a filament, and you run a current through it and it glows. And nearby, he placed a metal plate inside the light bulb. So when he evacuated the tube of the bulb, it's a near vacuum inside, any light bulb or any vacuum tube. The filament is the source of the electrons. He found that when he put a negative charge on the plate nearby, nothing would happen. But when he put a positive charge on the plate, something very strange happened. And it's this. The positively charged plate would draw the electrons being emitted by the filament, and a current would flow through the vacuum tube. This was the very first rectifier. It would only conduct in one direction, which is to be expected. The electrons can't come from the cold metal and go to the hot electrode. They can only come from the hot electrode, evaporate off, and stick to the plate. So, thermionic emission. Now, oddly, this is also the start of another industry, the vacuum tube industry, because there was a fellow by the name of Lee De Forest, and he took Edison's idea of the electrodes in the tube, and he added another electrode in the middle. And he used the filament emitting the electrons, the plate capturing the electrons, but in between he had a grid. and they often called it a grid, like a piece of screen wire. And when he placed a charge on that grid that was negative, it would interfere with the current flowing through the vacuum. And it could be controlled by an extremely faint signal, and it would amplify it. And so the audion was born, the very first amplifying tube or vacuum tube. Um, Later generations became more complex. But what was important was, for the very first time, you could literally amplify the human voice using a vacuum tube. And it also made audio systems and compact radio transmitters and receivers very, very possible. And so a whole birth of industry happened because of this thermionic effect. So what's so important about it, and how do we put it to use? If you were to have a device like that vacuum tube with a little voltage on it, and you were to place it near a source of heat, heat it up a lot, you wouldn't need to have the heat of a filament running through it. The heat of whatever, it could be a fire, it could be a hot device that you're stuck up against, it could be sunlight driving it, focused in a lens. Any source of heat sufficiently hot enough will cause the electrons to be emitted and go to that charged plate. And in the course of events, you develop a current of electricity. The amount of current flowing in this device can be from 25 to 50 amps per square centimeter, which is just a little guy about like that. But it's usually around a volt and a half. So you have to transform it to a voltage you can generally use. Nothing wrong with that. Simple thermionic generators are easy to make, but they're poor in efficiency, and they usually use a material such as cesium metal, which evaporates easily and ionizes easily. So what do you do with it? Well, suppose you need to make power. You have a source of heat, and you don't particularly care about the efficiency. You just need good, stable power. This is something that has been used for many years, for instance, by the Russians. Soviet military satellites used the trick of thermionic generation. They had something known as the Topaz series of compact nuclear reactors. And so the reactor would provide the heat to heat up the emitter of the electrons in the thermionic device. And the reactors would be hybridized with a series of these thermionic devices stacked in there. And when they pulled the control rod out and the reactor got hot, a lot of power would be generated. So the Topaz reactors were orbited in Soviet military satellites from 1967 to 1988. So believe it or not, nuclear reactors have been flying in orbit for decades, and they generally use these thermionic devices. There are other ways to do it, and obviously you can think that if you could make it more effective, more efficient, you'd have a source of power based on nothing but a little heat. And again, you don't have to boil anything or evaporate anything or run any turbines. It is a solid state device, essentially. Cogeneration is the ideal use for something like this. Suppose you have a gas burner or an oil burner or even a wood stove, and you place thermionic devices on them, and they're heating your room, they're heating your home. Then in the process of generating the heat for your home, you literally can be capturing electrical power and using it. And again, it doesn't have to be terribly efficient. Similar devices called thermovoltaics also exist. Now, everybody knows what a solar cell is, a photovoltaic cell, implying that light makes the voltage. And that's exactly what happens. In this case, it's a thermovoltaic cell. And thermovoltaic cells are made of specialty materials that easily emit electrons, and they form a diode junction with two dissimilar materials stuck together, and a current can flow through them. Well, in this case, heating one side and cooling the other side creates a pretty strong flow of current, and you can harvest that. There were numerous survival lanterns that would burn a little bit of gas or a little bit of oil, and it would provide enough heat for you to cook a small meal and enough light to see what you were doing. But simultaneously, in the exhaust stack of the lantern was a whole series of these junctions, similar to thermocouples. And they would generate an electrical current that could operate a radio transmitter, for example, charge some small batteries. And this was another Russian tool used for survival, a small lantern that provided heat, light, and electrical power, in one go. And really, if you were pushed for it, you could burn wood to operate the thing. So let's have a look at that. Is there a similar device in use in your home? The answer is absolutely yes. If you have a gas stove or a gas heater or anything with a pilot light in it, there are two special parts inside the gas valve. There is a valve that is held open with a solenoid. That's just a magnetic coil, basically. A coil with a piece of metal that it sticks to it like an electromagnet and holds the valve open. And B, there is a stack called a thermopile. The thermopile is a whole bunch of little thermocouples hooked together, and I'll talk about that in a second. And it generates enough voltage and enough current when heated to hold the gas valve open, because the current flows through the little magnet coil and holds the valve open with a magnetic field. If the flame goes out, the current stops flowing and instantly that valve snaps shut. And that's how you make a safe pilot light. So what is a thermopile and where do I get these magical devices? Well, many people who work in heating and cooling are familiar with devices called thermocouples. A thermocouple is two pieces of wire, basically, that are made of two different alloys. And different metals, when put together, have something known as a different electronegativity or potential voltage. And when you heat them up, the differences in the metals allow a current to flow. Now, this little bit of current can be measured and used to read the temperature. Well, that's what a thermocouple does. It's a couple of wires twisted together or welded together, and it makes a tiny bit of voltage and a tiny bit of current. And by reading it, you can see what the temperature is. And so most of the thermal sensors you see in industrial processes are thermocouples because they're very robust, they're difficult to destroy, and they're as simple as it can possibly be, two pieces of metal stuck together. Many years ago, it was discovered that iron and copper, when welded together or soldered together, would produce this thermocouple effect. And the trick is you need a difference in temperature. You can't simply make the whole thing hot. You have to have a hot side and a cold side. So you take a pair of thermocouples, welded together copper and iron. One is at the focus of some heat generating system, and then in line with it you have copper and iron hooked the other way around. So the copper is on this side, the iron's on this side. And then the iron runs down to the other iron side, which is welded to another piece of copper. It's stuck in some ice water. This side is heated by a flame or by focused sunlight or by some other source of heat. And you get essentially free electricity out of it. Again, the efficiencies of thermocouples are really terrible. But for many operations, they're the only game in town, and they're very easy to put together. So if you took a whole stack of little thermocouples, let's say you stack 10 of them up in series just like a battery, you'd get 10 times the voltage at the same current. So here's what you do. You make a thermocouple for hot and a thermocouple for cold, and another from hot and another for the cold. And you wire them in a zigzag fashion, back and forth. So all the hot thermocouples go, let's say, over a candle flame, and all the cold thermocouples go on a heat sink or something cold, like ice water. And from this, you can develop enough voltage to operate microchips, for instance, or small devices, kind of like the tiny little solar cell, the photovoltaic cell, in a pocket calculator. It does the same thing, but using heat. So now this is very interesting. A whole stack of thermocouples put together like this is called a thermopile. And if you were to open one up, it looks like a long metal rod, like a little pipe. And all the hot sides are on one end, and all the cold sides are on the other end, and two wires come out of the bottom. They pot the whole thing in epoxy or something thermally stable. Usually, if it's going to be heated with a flame, they'll put some sort of mortar inside there so it can't possibly burn. Fire brick compound is similar to what you'd probably use. Ground up oyster shells because they have magnesium carbonate in them. And that's what a lot of fire brick is made out of. It's very highly temperature resistant. So thermocouples, thermopiles, you can make a little heat. Thermionics, better device, better efficiency, and more robust in many ways. Now, this leads us to something called the Seebeck effect. If you have two materials that you can stick together to form a diode junction. And that's a device in electronics that allows the flow of current in one direction, but blocks it going the other way. It's a rectifier. If you take a stack of these devices, so all the hot sides are up and all the cold sides are down, and you sandwich them between two pieces of metal, perhaps, or ceramic, you don't want to short them. So you'd use a ceramic glued on one face and a ceramic glued on the other face, and you'll end up with a little rectangular, basically a plate that has dozens of these little elements stuck inside and a pair of wires. When a current is run through it, it does the same thing that the water droplets do when you step out of the shower. All those little modules pump the heat in one direction by spitting out the most energetic electrons in one direction. Well, what this does is it pumps the heat to one face of the device and leaves the other face cold. Now, if you've ever seen the small battery-powered refrigeration units, it's basically a small styrofoam box and a connection for your car battery, perhaps, and it chills your beverages. It's a solid-state refrigerator. The efficiency is poor, but they do the job with no moving parts, and this is an amazing and positive thing. The simpler something is, generally the better it is. And simplicity really is good if you're in a survival mode or if you have a limited amount of weight you can carry. And so these thermoelectric coolers are basically the inverse or the cousins of thermionic generators. So why is this important? Well, it happens that using semiconductor methods of manufacturing, tiny little microstructures can be created in a wafer that spit out electrons very, very easily. So literally changing the structure of the material can change its efficiency. Think about this. You shuffle across a rug on a cold winter day, you reach out and you grab the doorknob and it knocks the heck out of you. Why is it that that doorknob would do that? There's a very interesting reason. A smooth curved surface retains its charge very easily, whereas a pointed surface, like the tip of this pencil, has a very tight curve to the end and it emits a charge very easily. If you will look at lightning rods, you will see that they have a spine at the top or a number of spines around them. Why? Because these easily neutralize the charge in the air around the building to ground, and it eliminates a lot of the current in the lightning in many cases. A smooth, shiny ball would be the worst thing for a lightning rod, and it would basically destroy itself after 2 or 3 hits. So you want something with a lot of spines and curved surface area to dissipate the charge. Well, let's just carry that to the thermionics idea. So you end up with a small cavity with a vacuum. On one face is a micro-machined series of spikes on a wafer of semiconductor material or a metal, perhaps. On the other side is the metal plate, and you apply a small voltage. Now, when you heat the device up on the spike side, it radiates electrons, and you have a source of current. So this is the whole principle. We're now finding new materials and changes to existing materials. For instance, cesium, as I mentioned, was the metal most commonly used in thermionic devices. If you add a little oxygen to it, suddenly the efficiency goes way up. It causes something called recombination. It provides a ladder for the electrons to easily move through the process. What this means is that with minor variations in design, we're finding better efficiency, and with new materials, we're finding better efficiency. And very soon, it might be quite feasible to create a lot of your electrical power strictly from waste heat. So if you're heating your home or your building with natural gas or burning something, that device can be placed up against your furnace or near to it and can create a flow of electrical power to keep your batteries running and keep your building lit. So this is wonderful. Generate plenty of heat and end up with electricity as a bonus. Thermionics, very, very fascinating things. So if anybody has to ask any questions, by the way, the lines are open and we'll be right here to take them. I found a lot of interesting things you could do with thermionics and thermocouples and other devices. And one of the things you can do, you can wind a coil out of a lot of wire, and it looks like a bobbin, basically. If you're familiar with sewing, you know what a bobbin looks like. You place thousands of turns of very fine wire on a bobbin with a metal core in the middle, like an iron rod. And soft iron works very well for this. It concentrates the field. This device can be driven by that iron and copper soldered thermocouple junction. And test items that I've seen like this can create enough magnetic force just from sunlight being shined on it with a lens to pull over 1,000 pounds of force on a metal plate. This is amazing. You could use power from the sun to literally pick up 1,000 pounds with next to no electrical connections. It's a simple cable at this point. Of course, you need to use copper because you need the lowest possible conduction, and you need to use the lowest possible resistance. And the thicker it is, the better, the lower the resistance of your wire is. So if you'd like to try some experiments with that, go online and look up things like the Seebeck effect, Seebeck, and look up thermocouples. And you will find that there are a number of recipes for thermocouples, and they're all very effective in different regimes of temperature. Some work better at high temperatures, some work better at lower temperatures. And the best sort of thermocouple wire, J or K thermocouple type, if you look that up, you will find that it's a mixture of nickel and other elements. Like Alnico is aluminum and nickel and cobalt, for instance. They used to make a lot of magnets out of that in the past. So you can find chromel and alumel as the alloys in most thermocouples these days. Chrome and nickel and aluminum and nickel. And those two dissimilar metals coming together create a nice standard constant amount of voltage based on temperature. So that's similar to, it's not the same as thermionics, but it's closely related. And it's certainly something you can experiment with a lot. I built, as a child, a small device that powered a tiny radio by making a whole stack of thermocouples and radiating them out like the fan of a heatsink, placing all the junctions for the hot side on a candle flame and all the cold junctions out here in the free air. And it actually generated about 5.5 volts of electricity and was enough to run small electronic devices. And the other thing you can do, if you're adept at electronics, you can take a small voltage and you can multiply it through an oscillator circuit. And I won't even get into the technical details of that, but it's simple enough to do. I've seen kids do this stuff as part of a science fair project. So what do we see for thermionics in the future? The way it looks right now, it's quite possible within the next 3 years we should have commercial thermionic generators available that you can use, as I was saying, on your heating system in your home. And it's going to be particularly effective if you have a great source of waste heat. One of the things that these are very good at is bottom end recovery or cogeneration. In cogeneration, you're performing a task and getting something out of it, but at the same time you're also able to scavenge the waste end. So if you're running an automobile, for instance, the engine is running, it's running your generator, and the generator can harvest enough power to charge up your battery, run all your appliances and everything like that. You're generating not just the movement of your vehicle, but also the power for all the electrical devices. Cogeneration is like that. You have more than one function happening at once, and thermionics are ideal for that. One of the things you could do, if you really wanted to experiment with it, everybody knows that the catalytic converter in a car gets exceptionally hot in order to operate properly, usually around 500 to 700 degrees Fahrenheit. So what if you put a few thermopiles or thermionic devices on your catalytic converter? You should be able to harvest a few amps of power out of the thing, a few amps of current, and with the proper circuitry, you could step it up and run more things, charge more batteries, do whatever you want to do. So that's just an idea. Now, I do a lot of experiments, and I strongly encourage everybody else to experiment. So thermionics, definitely look it up. I think it's going to be a big up-and-coming thing in the near future. And also thermovoltaics, like photovoltaics. Thermovoltaics do the same thing. They use different materials. In a thermovoltaic, you don't have to apply an excitation voltage like you do with a thermionic device, But the thermionic devices give you basically a lot more current. And it really depends on the design, to be honest. But look it up. Look up thermionics. I think you'll have a lot of fun with it. I'm also going to go ahead and encourage people to join Schultz Laboratories and the Universe Science Center. Go to our page, click on the link, become a member. We also have new classes starting tonight and every Monday for the next 6 weeks. And this is on Meta World. Now, Meta World is an investigation into where we're going and why. We start with sticks and rocks and fire, and we're migrating toward nanotechnology. And I highly recommend the lessons. They're at 9 p.m. Eastern Standard Time every Monday for this and the next 5 weeks following. Tonight will be the first lesson, and we're going to talk about the beginnings of humanity and the fact that animals use tools and have simple language. And where do our abilities come from? What makes us special? Why do we see the world so differently than an animal does? Well, we're going to look at that in detail, and then later we're going to see how we develop pragmatic systems, how it's survival related, why we have the innate desire to explore and learn. The biggest difference, of course, for us is abstract thinking. And the ability to talk about something like thermionics demonstrates that. This is an idea that you might not have heard of before. We place this idea in your mind. You can go out and learn about it, research it, apply it. That's one of the cool things about being a thinking upright ape. It allows you to do things that other animals just plain can't do. And we also encourage you to help us expand our Universe Science Center, add more galleries, more content, and also give me some hints. What would you like to hear about? I'm going to continue to randomly generate new show subject material using the computer program that I created. And we're going to see if we can't put that on the air live so you can see the generation of the idea on the fly. Be a surprise to all of us. That'll be great. Again, keep in touch with us. Send us any emails to admin@schultzlaboratories.com if you have any questions. And also, please do try to make the world a better place. I focus on this because we often see what looks like dark times around us. And we have to realize that it only gets as bad as we allow it to. We each and every one have an obligation to be of support to our friends and our neighbors, and even people we don't like. We don't have to treat them badly. And you know, this series, the Randomizer, is a small contribution I make because it makes people think and it gives you a little inspiration, something to be a little more happy about. The world is an interesting place, and we have millions upon millions of ideas, any one of which, in the right ears, could change a life or more. So this is one of the reasons I enjoy doing this. We also want to get some homeschoolers on board with our galleries, and let us know if you have specific educational requirements. If you need a room where we demonstrate the operation of an industrial machine, we can do that. If you have a company that has to train people to operate a vehicle or something, we can do a simulation for that. And they can put on their Oculus and drive around and learn how to make it happen. I can't stress enough how important the concepts of virtual reality will become in the near future. And it's not just because of entertainment, but it's because of business. If you consider how many people were working virtually over the last year and a half, 2 years, you'll see the importance of being able to interact in a natural seeming environment. And we're probably going to do some talks about that stuff pretty soon. Let us find inspiration in the new things that are in our lives. For me, thermionics isn't a new idea, but I know for many people it is. We can literally take waste heat, convert it into usable power, and do something with it. And I also would suggest look into photovoltaics, look into thermovoltaics, see how you can create a little extra power. I don't know if you're a tinkerer or not. I hope that you are. Get some material together, make something you can take out and test in the yard, and have fun with it. You know, every one of us has the ability to become a mad scientist if we wish. We just have to find something that inspires us, get out our saws and our drills and our soldering irons and maybe even paintbrushes or clay or whatever it is, and make it. Well, this has been the Randomizer. for Monday, January 31st, 2022. Thermionics is our concept tonight, and I hope you've enjoyed the show. Everybody take care, have a wonderful evening, and come back tomorrow for our next show. We'll find out what it's all about then. And thank you.